All right, so you've hired Probert to stand at point P, and I just want to reinforce Probert's identity. Probert is a positive unit test charge. So positive unit means the charge on Probert is E, one fundamental unit. Positive means polarity. Test charge is test charge. Test charge means Probert can report the following. Probert is going to report the electrostatic force at a given point, the electric field strength and direction at a given point. And now we're asking Probert to report on voltage at a certain point. And there are three terms that mean the same thing. Voltage means the same thing as potential. And there's another term that's used interchangeably, potential difference. So a lot of times you hear one or the other of these terms used: potential difference, or voltage. To be honest, I do kind of try to use voltage just to avoid confusion, just to maybe settle on one term. However, the term potential difference is arguably more descriptive, because what is voltage? Voltage basically a change in pressure. And again, that rings a bell, because in the lecture video for chapter 24, there is a analogy between voltage. There's a plumbing analogy. So what does pressure do in water? Pressure difference. When you turn on your faucet, so walk into your sink, turn on your faucet in your sink, and water starts to flow out of the faucet. And that's because there's a pressure difference. The pressure on the other end of that water supply is greater than the pressure on the outside or near surrounding your faucet. So a pressure difference is analogous to voltage. And again, this is part of the many plumbing versus electricity analogies that have been building since chapter 21, I think. All right, so Probert is standing right here at this point, and we've asked Probert to tell us what is the voltage, what is the electric potential at that point. So it's just sort of like how much, what kind of oomph are you feeling, Probert? So if we were talking to Probert, say, Probert, go stand at point P and tell me what kind of electric potential energy oomph are you feeling? So it's that oomph that we're asking Probert to talk to us about. All right, so the expression for the electric potential, also known as voltage, due to a point. So we have let me backtrack just all right, so voltage is, change in voltage is, voltage is defined as potential energy, electrostatic potential energy per charge. And if we deltaize that, or if we look at the changes, change in voltage is defined as the change in electrostatic potential energy per charge. And usually we're interested in tracking the changes in values versus like their flat out absolute value. Not all the time, but typically. So this is the definition. This is the definition of voltage. So this is the oomph per charge. Voltage is the oomph, which is that, per charge, which is this. All right. So this is what voltage is defined as. And not to backtrack too far, but basically for a point charge, voltage is KQ over R. KQ over R. This is for a point. And we're going to do something very similar in this chapter that we did in previous chapters. We're basically going to say, I don't know how to deal with anything other than a point. So I'm going to deal with a point, and then I'm going to stack them all together to figure out what's happening macroscopically. All right, so just before I leave this, voltage is potential energy per charge, and potential energy is basically force per, well, I talked about something known as the little yellow ball analogy. Let me postpone that. Let me just keep going with this and then I'll backtrack. And maybe I won't backtrack at all because I'm going to have to let you guys pick this up in the lecture video. So for a point charge, this is the expression for voltage, but I have three point charges. So I'm just going to index these: Q1, Q2, Q3, Q4. So the voltage field, and one thing I should mention, voltage is a scalar field. Voltage is, it's not a vector. This is maybe one of the big reasons why chapter 24 is a little bit easier than chapter 22 and is easier than chapter 21, 22, and 23, because voltage is a scalar and you can actually have a scalar field. Whereas the electric field that we've been dealing with in chapter 22 and 23, the electric field is a vector field. So whenever you have vectors, you have to worry about magnitude and direction and decomposition and all of that stuff. Whereas voltage is a vector field. Why? Look at its definition. Energy is always a scalar. Energy is not directional. So energy is always a scalar. Charge is always a scalar. Energy is always a scalar. It's not like you ever find somebody saying, well, my energy is 13 joules at an angle of 30 degrees with respect to the positive x-axis. So this is, I think, why doing voltage analysis is sort of a little bit lighter weight. All right, so, but we do have four source charges here. So Probert is going to feel this. Probert's going to say, the voltage I feel at point P, this is Probert talking, is the voltage due to charge 1 plus the voltage due to charge 2 plus the voltage due to charge 3 and the voltage due to charge 4. So this whole thing, whenever you kind of do this additive approach, it's sort of the term is superposition. So let's just break things up into their tiniest components and see what they add up to be. So Probert is going to feel, and I'm going to follow the subscripts, K Q1 over R1 plus K Q2 over R2 plus K Q3 over R3. So again, just kind of staying in robotic mode, just very methodical, plus K Q4 over R4. And then now we can start to personalize this for the situation here. Okay, so let's just keep going. VP equals K, well, okay, equals K, got it. Q1 is just going to be that positive Q right here. So here's Q1. It's a positive Q. I do have to, this is not vector. So you've heard me say a lot of times, let the angle, let the sine of theta or the cosine of theta determine the positive or negative aspect of a component. But we don't do that here because there are no sine theta, cos thetas when we deal with point charges like this, because voltage is a scalar field. So we do have to be aware of the positive contribution or the negative contribution of a point charge. This point charge right here, for example, just sticking with Q1, this produces a positive voltage field. This creates a positive voltage field. So Probert, whatever Probert senses from Q1, it's going to be a positive oomph. Okay. So what's the distance between Probert, which is right here, and Q1, which is right here? And that is distance D. So just, again, being very mechanical here, this is the voltage due to charge 1, K plus Q over D. Here's the voltage due to charge 2, which is also the same thing. So it's K times the magnitude of the charge, the magnitude and polarity of the charge, magnitude and sign of the charge. What's the distance between probert and Q2? That's also D. Then on to 3. 3 is going to be K times negative Q, and the distance between Q3 and probert is D. And last but not least, Q4. Q4 is also a negative Q, but the distance between probert and Q4 is 2D. So let's just pull out some common factors. The voltage that probert will be reporting, I can pull out a K. If let's see, can I pull out a KQ over D? If I pull out a KQ over D, then this is going to be 1 plus 1 minus 1 minus 1/2. If I've done that right. Okay, which equals KQ over D times 1 plus 1 is 2. 2 minus 1 is 1. So it's 1/2. I think that's the answer. All right, so let's actually plug in units. The voltage at probert's location is K 8.99 times 10 to the 9th Newton meter squared per coulomb squared. That's K. Q is given as 5.38 femtocoulombs, which is negative 15 coulombs. KQ times 1/2. So this would be times over 2 times D, and D is 0.0384 meters. And then let's get an answer there and then look at dimensions. Okay. So the answer is correct, getting the right answer, but we have to do dimensional analysis just because that will be given to you as a specification on exam 2 and all of the exams. So from a dimensional point of view, I have newtons meters squared over coulomb squared times coulomb in the numerator. In the denominator, I have meters. So this is the same as newtons. I'll just go in piecemeal fashion. Newton meters squared over meters coulombs equals a Newton meter per coulomb equals a joule per coulomb equals a volt. How do I know a joule per coulomb is a volt? By the definition. Here's the definition of voltage. Voltage is the amount of energy per charge. So just go back to the definition. Voltage equals joules per coulomb. So from a dimensional point of view, dimensional analysis, correct. I do get the correct units, and I do have the right number, 6.29 E minus 4 volts. So that's it. This is our very first voltage problem, very first introduction to a scalar field. Voltage is the amount of oomph that a given charge would feel at a point. So just think of water pressure. If you want the water to come squirting out of your faucet at a greater rate, stronger. If you want a stronger flow, then create a larger pressure difference. Okay, that's quiz 1. Let's go on to quiz 2, 24-2. Okay, it's now 8:24. Chapter 24, quiz 2. Chapter 24, quiz 2. So this is a different type of problem, obviously, because I'm not dealing with simple point charges. And the progression we take here is just like the progression we took in chapter 20, chapter 22, and in some ways chapters 23. But there is a progression. I'm hopscotching around a little bit just because, again, a lot of these problems are solved via deep dives. But just to repeat, we're dealing with, here's our continuum we're dealing with. We're going to deal with the voltage due to a point, the voltage due to one or more points, the voltage due to a line of charge, the voltage due to a surface charged surface. And last but not least, we're also going to be dealing with potential energy, electrostatic potential energy. So these are the major categories in chapter 24. We need to figure out how to calculate the voltage at a given point due to a point or a system of points or a bunch of points glued together like what we have here, or a surface like a plate, a circular plate or a rectangular plate, stuff like that. And then on the flip side of this chapter is potential energy considerations, which is always sort of the final destination. When you do energy analysis, you know you've kind of arrived at the highest level of analysis because it's the most powerful analysis. It's the most utilitarian type of analysis. So I have a system of points. Probert is standing there at point P. The figure shows a thin rod with a uniform charge density. That's critically important to say. And I don't know if I'm doing a problem. Let me just see. Am I doing a problem where the charge density? Yeah, I am. So that's good. In this case, the charge density is uniform, but that's not always the case. So make sure you read all of these terms carefully. This is a thin rod with a uniform charge density of 4.4 microcoulombs per meter. Evaluate the voltage at point P. So yes, Probert is standing right here. So as mentioned, I don't know how to deal with anything other than simple points. So we did this very same approach in chapter 22 and prior to that. In the physics class you had before this, you should have done this as well. All right, so first thing I'm going to do is I'm going to identify a little sample point. I'm going to say right here, this is a super teeny tiny little point right there, right like that. Okay, so I'm doing this because I can deal with points. I know the voltage due to a point is KQ over R. So this is my starting point. So I'm going to identify a point size point, a DQ. Identify a DQ. How big is DQ? It's infinitesimally small. Infinitesimally small. And if it's infinitesimally small, it means it's a point. Infinitesimally small point. That's what it means to be DQ. If you're called DQ, you're infinitesimally small. So the name of this point is DQ. Everything has a name. The name is DQ. The size of this point, we have to worry about size. The size of this point is dx. All right, and that's what I'm showing here. This is dx. The location, so we have to name it. We have to talk about its size. We have to talk about where it's located. Let me just move this over. All right, the name is DQ. The size is dx. The location is right here. This point is located right here, I guess. I guess I'm calling that 0. There it is. Where's this point located at a distance x away from what I'll call the origin here? 0, 0. All right. So I've identified a point and I've specified this point. And I'm going to repeat this. The goal of solving complex systems in a physics course like this is to specify an integral, in terms of geometry and material properties, geometric and material properties. So even if, like, let's say you fell asleep and you slept through this whole lecture, if you only remembered this approach right here, this strategy, it could be argued that you're good to go because you know how to do integral calculus, and you're just going to need to capture as many geometric and material properties as you can. So that's what I'm doing here. All of this is prep work towards that end. The name of the point is dq. The size of the point is dx. The location of this point is x. I should also indicate this, the location with respect to Probert, because Probert is asked to report what's going on. So this is the location. I guess I'll call this R. That's really, to me, that's like the more dominant. I don't care what's happening. I don't care about the voltage at the origin. I care about the voltage at Probert's location. So anyway, it's all good to go there. So now that I think I've specified the rudiments of the point, the name of the point, the size of the point, the location of the point, now I get to use this. Once again, the voltage due to a point is KQ over R, generically speaking, but now I'm going to deal with differentials. So I'm going to call this dV equals K dQ over R, because I'm dealing with a super teeny tiny microscopic point, which basically makes just a differential contribution. I'll integrate. Once I get this set up sufficiently, then I'll glue all of these points together. And what is the mechanism to glue all of these points together to see their cumulative macroscopic effect? The answer is the integral. All right, so I'm feeling good so far. I'm going to use this. I remember that linear charge density is defined as charge per length. This is not the first time you're seeing this term. Linear charge density is charge per length. From a macroscopic view, it's the total amount of charge on that rod over the rod's length. From a microscopic view, I could say dq, charge per length, over dx. And because of this word, uniform charge density, because you see this term called uniform charge density, whatever this value is, whatever is true macroscopically must be true microscopically because of that uniformity requirement. This is what happens when the charge is uniform. Wherever I take a sample, I could take a sample anywhere on this rod, and wherever I take that sample, the density is going to be the same. That is not going to be true if it's a non-uniform charge density. All right, so I can then say, well, I'm going to just go ahead and express dq as lambda dx. What's my motivation to do this? Once again, I want to capture geometry and material properties. And you have both of those right here. This is a material property. Lambda is a material property. Like you have a certain material that has a different charge density. Charged lucite has a different charge density compared to charged aluminum. So that's a material property, and this is the geometry. So that's my motivation for representing DQ this way. And I'm just going to keep going until I can't figure out any ways to drill down deeper. So I'm going to update. So here's my new dV. I have dV equals K lambda dx over R. R is the distance between probard and this teeny tiny point charge. So I'm going to just go right to here. dV equals K lambda dx. And here's R. R is going to be the square root of x squared, or I guess d squared plus x squared. That's it. That's it. So that's my expression for dV. Can I do any more drilling down here? So I'm just going to step back before I go down a path. What if I did something wrong? I don't want to waste time. So this is K dQ all over R, K dQ over R, Pythagorean theorem. I'm feeling okay about that. I don't need to deal with sines or cosines or anything like this. I don't need to decompose this. So I guess I'm good to go. Now we just have to solve this integral. So let me do number 6. Okay, so number 6. So I've specified that as much as I can. I can't think of, I'm out of clever ideas about how to drill down any more with this expression. So time to integrate. And if I can't figure out how to integrate this, then I'll, that will deal with that scenario should it arise. But the voltage at point P, which is where probert is standing, is just going to equal the integral of dV. It's like the integral of dx is x. And now I have the integral from where my limits of integration. I'm going to integrate from L. It looks like I'm going to go all the way to L on my top, and then my lower limit of integration, my boundary conditions from L to D. Actually, that's not right. L to L minus D. Big difference. Okay. So of K lambda dx over square root of d squared plus x squared. Okay. So you can integrate that, or what you'll see with exam 2, is a table of integrals. Let me show you what that's going to look like. Exam 2, and maybe exam 3, I think too. Let me just get a picture of what this table of integrals is going to look like. It's in the back of your textbook, which you have access to in Wiley Plus. And it will look just like, oh, there. It will look just like this. This is, I'm just going to Xerox this page and give it to you with the exam statements. And I think it starts, I think this will be given to you for exam 2, exam 3, and exam 4. So now the question is, do any of these integrals have the same form that we're dealing with right now? And you could argue that you don't need, I know how to solve this integral without this sheet, but the assumption is, well, whatever the assumption is you know how to integrate, but this table of integrals is provided. So I see it there. It looks like number 17. It looks like number 17 is in the form that we're dealing with right now. So I'm going to take a little snapshot of step 17. Here's step 7, integral 17. This is integral 17. I'll bring it into the notebook here. And use it. So this is my integral. All right. Okay. 10, 3, 10 to 7. Okay. Number 7. The voltage at point P is going to equal to, well, apparently when I solve this integral, I'm going to bring out the constants first. K is a constant. Lambda is a constant. And I erase that dx. Okay. So I'm bringing my constants to the left of the integrand. K comes to the left of the integrand. Lambda comes to the left of the integrand. And I'm just left with this integral. Dx all over square root of, I guess I'll write it like this just to be consistent with that integral number 17, x squared plus d squared from L all the way down to L minus D. Well, let's check this limits of integration. So this is how I think about it, just to check myself. Let's just say for the sake of conversation, L is 10 meters and D is 2 meters. I want to integrate from 10 to 10 minus 2. Okay, that's fine. Just a sandwich. You could ask yourself, what's the difference between L to D versus L to L minus D? So that's fine. All right, so I'll let you figure that out. All right, so now I have the voltage is K lambda times natural log of x plus square root of x squared plus d squared. So instead of using A, we're using D. So I'm just going to say, instead of using A, we are using D. And here's our limits of integration. I can just do that. Interchangeable from L to D. Fine. These are one and the same. All right. So voltage is K lambda. This is going to get a little bit fine-grained. Natural log of x. Natural log of x. So this would be, this is going to be L plus the square root of L squared plus little d squared minus the natural log of d plus the square root of d squared plus little d squared. Okay. Let me check that. K lambda, natural log of L plus L squared plus D squared minus natural log of D plus root of D squared plus D squared. Okay. So let's plug in the givens. They are saying the following. They are saying right here, little d is the same as big D is the same as L over 4. All right, so with that substitution, I'm hoping that makes things simpler. Number 10, voltage is K lambda, natural log of L. Natural log of L, that's fine, plus the square root of L squared plus little d squared, and little d is L over 4, so this would be plus L squared over 4. Okay. minus natural log of big D, and big D is L over 4, plus big D squared, root of big D squared, which is L squared over 4, plus little d squared, which is L squared over 4. Okay, I guess that's it. And let me just double check because I'm paranoid. K lambda natural log L plus L squared over 4. Maybe just do this. Okay, that's not nice. All right. Okay, I guess that's good. So let's see. Do we know all of this? I'll let you guys deal with the algebra when we get to it. But do I know the value of K? Yes, 8.99 times 10 to the 9th. Do I know the value of lambda? I do. Little lambda sidebar. Lambda sidebar. Lambda is charge per length. And because this is uniformly charged, lambda is charge. Unless, did they give us lambda? They did. So I don't even need a sidebar. I know lambda, it's 4.4 times 10 to the minus 6 coulombs per meter. So I do know K, I do know lambda. Do I know L? L is, I don't know L. So here's what I'm going to hope. I don't know what L is. I'm going to hope it cancels. I'm going to say, I hope L somehow cancels. Because I don't know what L is. I know everything else except for L. So maybe the last thing I'll do before I let you guys take over on the algebra, I'm going to remember log properties. The voltage at that point is going to be K lambda natural log of, this would be my numerator, natural log of L plus square root L squared plus L squared over 4. I'll write it like that. All of that over L over 4 plus the square root of L squared over 4 plus L squared over 4. Okay. Sorry. There. Okay, let's see what you get. We know all of these values. We know K, we know lambda, we don't know L. I can see here L's will cancel. The L's will cancel. The end of the match so people can catch up with this. But more than anything, I mean, this is turning into like just an algebra endurance test, which is kind of, I always worry a little bit about the problems that require a ton of algebra because it's so easy to focus on the algebra and not on the overarching strategies and approaches. This is the overarching strategy right here. This is basically what you did. You basically instantiated this approach. You set up an integral in terms of its geometric and material properties and let her fly. Okay, and this is a very common approach. You've seen this before, you'll see it again. Great. So again, I think all of us had little d equals big D equals L over 4. And I think I was good up through step 9. Step 10 is my first mistake. So steps 10, D squared, if I have to replace D squared with L over 4, this should be L squared over 16. And similarly, this should be L squared over 16 plus L squared over 16. which means step number 11 should become L plus, and this is 16 over here, and this is L over 4L, so there. And this is right. So the final answer here is the voltage equals K lambda natural log of L plus square root of 17 over 16 L squared all over, oops, not writing very neatly, all over my denominator, which is L over 4 plus the square root of L squared over 8. And that, if you cancel out all the L's, V equals K lambda natural log of 1 plus the square root of 17 over 16 all over 1/4 plus square root of 1 over 8. Let me just double check that now, just because I'm paranoid. All right, so 17 divided by 16. Yep. Okay. All right, works for me. Works for me. So again, you guys, this is this needs to be said. Those of you who have decided just to look up the answers, let me just say this again. You've basically cheated your way into getting a small amount of points now, but it comes at a price. And I'm saying this, and I'm not going to swear that all of you did it, but it does seem kind of funny that a lot of you got this answer really quickly, and yet you were reading off a mistake. And the only possible explanation for that could be, well, maybe you just were completely independent of me. You did your own thing. You didn't make a mistake and you're good to go. So that's let's pretend that's what you did.
Well, Professor, I just plugged in step 11 into my calculator and just did like 1/4 completely squared, or like 0.25 squared. So it did all that work for me. And then it just spit out the proper answer.
Okay. Maybe that's what it is. I see what you're saying. So instead of dealing with L squared over 16, you just did L over 4. You plugged in L over 4, got a number, and then just squared that.
Well, I just did 1/4 as my value for L over 4, and then for L I did 1.
Okay.
So like I had it plugged in. So my value was 3 to the -6 coulombs. Like that was my lambda value.
3. Wait, lambda was what? 3 to the -6. What would the units be on that?
Coulomb meters.
Cool. Say again. What? Be careful. What are the units? Lambda is 3 e minus 6 coulombs.
Yeah.
No, that can't be. Lambda is charge per length. So if you have lambda as charge per length, you can't have the units of coulombs. What's the unit for charge?
Well,
just shout it out. Just shout it out. What are the units of charge that we use?
Coulombs?
Yeah. And shout this out. What's the
unit? Lambda would have to be coulombs per meter.
That's what I said. Coulombs over m.
Okay. All right, good. So your lambda was 3 e minus 6 coulombs per meter. Then what else did you have?
And then for the, I'll just tell you what I plugged into my calculator. My distance was L over 4, and that that was the only givens in the problem. Yeah. I did 9 to the 9th by 3 to the -6 log 1 over 1 squared over 0.25 squared.
Okay.
And then all that over 0.25 plus 0.25 squared, or plus square root 0.25 squared plus 0.25 squared.
No, I follow you. I see what you're saying.
Yeah, that's what I did.
Yeah, if you did that and you got the right answer, it's because you did it correctly. And I see what you're saying. So you and this is a good thing. You didn't completely follow my algebra. You didn't, you sort of stopped. You said you stopped at step 9, right?
No, 11.
Okay. You stopped at step 11. And again, you didn't do L squared over 16. You just did L over 4. And then you squared that value is what I hear you saying.
Yeah.
Yeah, which is fine. So good. So that explains it. So again, maybe I'm being paranoid here, but I'm just
Yeah, that's what I read.
Yeah,
When
and I'm just maybe I'm being
That's what I
paranoid, but I
read
just
too.
want to encourage everyone to shout out my mistakes when you see them. But if you work independently from me, that's good as well. Just say no to looking up the answers, and maybe nobody did that. So apologies if I've insulted anyone. But fight the good fight, which it sounds like you did, because that's a very I get what you're saying. All right, so do we need to talk? Here's my suggestion. Stop working on this problem now. And again, I will add stoppage time, because if you continue to work on it, which is commendable, it will have a cumulative effect in terms of you falling behind more and more. So let's do chapter 24, quiz 3. Chapter 24, quiz 3. Is now, let's see, it's now 8:56. We'll do this one and then take a break. Okay, chapter 24, quiz 3 is now available. And this is another step up in terms of complexity. So today, we have dealt with the charge due to a system of points. The quiz we just did is a charged line, basically, voltage due to a charged line. And a line means it could be a straight line, or arc. What do you get when you take a straight line and you bend it? You get an arc. So this could be a straight line or arc or hoop, basically. Those are all considered charged lines. And now we're graduating up to a surface. So that's the progression. This is a plastic disc. Let me get a picture. Let me go to the textbook. Let me get a picture of this, a better visual, a charged disc. There it is. Okay. Problem 31. There. Okay. Okay. We have a plastic disc of radius 40.1 centimeters, my numbers, is charged on one side with a uniform charge density that's given. So they gave us that material property. It's all about capturing geometric and material properties, and they gave us sigma. So let me just, sigma, Greek letter sigma, is charge, not charge per length. This is not a line of charge or an arc or a hoop. It's a surface. So sigma is charge per area. And is it uniform? Yeah, it is. It's uniformly charged, which means charge per area is big charge per big area. And if it's uniformly charged, it's differential charge per differential area. Okay, so that's where I'm once again going to quickly say that my little teeny tiny dq is going to equal sigma times dA. Okay, so I'm taking this same approach. I have to identify my little sample point charge. I'm going to say this is my little sample point charge right here. I'm going to take a super teeny tiny dq and just arbitrarily draw it somewhere within this charge region, like that, and then maybe like that. Okay. Not quite. Good enough. All right. What's the name of this charge? The name of this charge is dq. dq. What's the size of this charge? It's dA. The size is dA. What's the location of this charge? It's right here. It's little r. Well, the location with respect to Probert is right here. Here's its location relative to Probert. That's the location. With respect to the coordinate axis, it's located here. And we can just call this a distance r. It's a distance, well, it's a good name. It's a distance r away from the center of the disk. So I guess I'll call this r and I'll call this little a. All right, so it has a name, it has a size, it has position with respect to Probert. All right, so business as usual in that regard. I've named it and specified it. So once again, I know the voltage due to a point charge. It's KQ over R for a point. So I'm going to say, well, I still have a point, so I'm going to call this dV, which is the voltage due to an infinitesimally small source charge named dQ, all over, in this case, what's the distance between Probert and that patch? It's A. Okay, so this equals K sigma dA all over little a. All right, so now we have to wonder, what's dA? What's dA? So I'm going to do the whole birth of a radian conversation. I've done this before. This is, I'm going to draw dA from a top-down perspective. So here's dA, and I'm going to enlarge it. This is a blown up view of dA, that little surface patch, from a top-down view, so I can see it better. All right, come on, trouble. Good. So this is my dA element. It's super small. I'm going to remember birth of a radian. So I remember that theta is defined as S over R, which means S equals R theta. All of this is what I call birth of a radian. So this is just a little reminder about the relationship between angular measurements and linear dimensions. So S equals R theta, and I'm living in the differential world, so it's going to be ds equals R d theta. All right, so here's ds. I have to get real up close and personal with this surface patch. This is ds. All right, so this is a differential arc length. I have that as my arc length. How many of these arc lengths do I have? Let's count them up. I have 1, 2, 3. I have a whole bunch of these little arc lengths. And in fact, if I stack them up one on top of the other, like a stack of pancakes, if I stack enough of these differential arc elements, I am going to get dA. So how many of them do I have? I have dr of them. So I can say, I guess I'll stay purple for, I can say dA equals ds times dr. So let me just repeat that to make sure I'm right. I have I have one of these arc lengths here, and then I'm stacking them up dr thick. So dA is ds times dr, or because of my birth of a radian substitution, I can say that's going to equal r d theta times dr. Okay, so that's dA, r d theta dr. So I'm going to do this. Theta, so from this circle's point of view, this has all been snipped out. This is my only charged region right here. It says I only have this quarter of a circle that's charged. I removed, it says, and then 3 quadrants of the disk are removed. So I only have a quarter circle. Okay, so a quarter circle, well, I'm remembering, well, a circle is equal to 2 pi radians. So if one circle is 2 pi radians, then a quarter circle is going to equal pi over 2 radians. And you might have saw that like right away, but just don't want to assume anything. Pi over 2 radians. So in terms of my surface element here, I'm going to say dA equals r dr times pi over 2. Or maybe I'll just write it pi over 2 r dr. And technically you could say, well, I'm going to do it like this. It's r dr times the integral of d theta from 0 to pi over 2. This is being a little more formal, but that's it. All right, so now I'm ready. Now I've done a lot of this heavy work to specify that little surface patch, and it's time to proceed. This should go quickly now. Number 4, the voltage at point P is going to equal K. I'm looking right here. I'm looking at number 2 again. K sigma dA. dA is going to equal pi over 2 r dr all over A. And here's what A is. A is, again, Pythagorean theorem. A is going to equal d squared plus little r squared. And I should write, this is differential. Okay, so they're very similar to the last problem. This is definitely calculus-based physics, calculus-based engineering. This is why we learn integral calculus, is because we can deal with points, and then once we figure out what's going on with the point, we can glue it all together. So number 5, the voltage at point P is going to equal the integral of dV, which is the integral. I guess I'll throw my limits of integration here. I want to take all of these little surface elements from the center of the plate right here all the way out to the edge. So that's why I'm going to specify my lower boundary as 0, the center of the plate, all the way to big R, which is, again, collecting all of those elements from the center of the plate to the outer edge, the outer perimeter of K sigma pi over 2 r dr all over square root of d squared plus r squared. So let's bring out the constants. K sigma is a constant. So is pi over 2. Maybe I'll do it like this. Pi over 2 is a constant. K is a constant. Sigma is a constant. And I'm left with this integral of r dr all over the square root of d squared plus r squared. And we can solve this integral without the lookup table, but let's see, does the lookup table have this integral? Let me bring that back up again. here's the table right here. Okay. Do we see this integral here? No, I don't think so. Do we? So I guess we're going to have to use u substitution. Dx, no, x over, no. All right, so let's use u substitution. I thought it was here, to be honest, but it's not. All right, so calculus time. Number 5, number 6. Let u equals d squared plus r squared. That means du is going to equal 2r dr. So then my integral is going to be the integral. I'm going to have pi over 2 times k sigma integral from r to 0 of r dr, or 1/2 du, all over the square root of u. Okay, so again, I would say r dr, let's say here, du over 2 equals r dr. So let's keep going with this. This is going to equal pi over 4 k sigma integral from 0 to r of, I'll do it like this, u to the minus 1/2 du equals pi over 4 k sigma u to the 1/2 over 1/2, and then that's it. Correct. From 0 to r. Okay. Equals, yikes. No, this is fine. Pi over 4 k, this would be pi over 2. Pi over 2 k sigma u to the 1/2. U is d squared plus little r squared to the 1/2 from 0 to r. Okay. All right. So if there are no mistakes in this fine print, let's see what we know. We're ready to plug in numbers. I know the value of k. Sigma is given to me 6.53 femtocoulombs per meter squared. Yes. Oh, sigma. I know k. I know sigma. Do I know big D? Do I know big D? Distance. Yeah, I do know big D. Big D. Careful though. For me, big D is going to equal careful, 0.078 e to the minus 2. Because for me, big D is 0.078 centimeters. So it's 0.078 e minus 2 meters. But I do know big D. Do I know big R? I do know big R. It's 0.41. All right, so I know everything. So let's get an answer here and then take a break. Actually, let's do this because it's 9:13. I'll do see you at 9:23 a.m. See you at 9:20. So we can a break. Let me do this. I'm actually going to extend that. See you at an unheard of. It's now, because I know a lot of people are still working on the prior problem. See you at 9:30. All right, talk about quiz 3. And to be honest, I took sort of the harder approach here. I'm still hung up on that.
You reopened 2 again.
2,
Yeah, close.
I think 2 is open. Let me check. Quiz 2. Quiz 2, and if it's closed, I will reopen it. But
Said it was closed for me.
I'll probably reopen it after we're done with everything. Because again, I don't want to have I don't want to have a divergence of students who are keeping up and students who are falling behind. Because as soon as you fall behind, it's compounded. All right, so now chapter 2 is still open.
Can you change the time?
Let's see, I have chapter 24, quiz 1 closed at 9. Chapter 24, quiz 2 closes at 10. Chapter 24, quiz 3 closes at 10. And I can extend those if I need to. But right now, quiz 2, quiz 3 show a 10 a.m. deadline. And I'll leave it like that. And then I can reopen it when we're done with quiz 4, which we can start now. Chapter 24, quiz 4. It's now 9:42. So I'm glad you told me what you did, because that puts my mind to rest that that we're not using those nefarious lifelines. All right, so chapter 24, quiz 4.
I didn't even notice that you had made a mistake because I read it as the same way as the other guy.
Yeah, that's good. That's encouraging. Okay, chapter 24, quiz 4. The other guy is now open. You should now see it. Chapter 24, quiz 4 is now open until 11, which hopefully that's more than enough time. But these are pretty tedious, let's be honest. Tell me if you're not seeing what I hope you're seeing here. I think, let's see. Okay. This should be chapter 24, quiz 4. More, I mean, to be honest, full disclosure, more full disclosure. This is a triple dot problem, which means, I mean, almost all of your homework assignments and all of your exam problems are double dot. And those are degrees of difficulty. Triple dot problems are the highest degree of difficulty. Double dot problems are moderate, and single dot problems or no dot problems are the lowest. So this, I believe, is a triple dot problem, I think.
My quiz four.
This one,
my quiz 4 is showing the previous question as well.
Quiz 4. Really? All right. I'm looking at quiz 4 should be 2433. 1, 2, 3, 4, 2433. Okay, let me change it. Yeah, I see what you're saying. $24.33. Okay, so if you refresh, and let me know if you're seeing what I'm seeing, which is homework problem 2433. And if not, then I'm still doing something wrong. And I'll fix it.
It's working for me now.
Okay, thank you.
I'm saying the correct thing as well.
Okay. Yeah, that's always my mistake. All right. thin plastic rod. So this is similar. This is a, I think quiz. Yeah. Well, I know this is a triple dot problem. This might be the only triple dot problem, and I don't think it's that hard, especially when you digest. If you embrace this standard approach that you use for calculus-based physics and calculus-based engineering, these do start to look the same. And that's just a hurdle you need to get to get to that point. This is a thin plastic rod, and they mention they use the word plastic because plastic is not a conductor. And it's important to specify that because you can charge. You remember the pieces of tape? Last time in class, we were charging strips of Scotch tape. And Scotch tape is plastic, basically. You can charge plastic, but once the plastic is charged, the charges are not free to move around. So these charges, this is a thin plastic rod, and is it uniform? It's non-uniformly. So anyway, that's quite the wrinkle. But this is a charged plastic rod. Once charged, these charges cannot move around, as opposed to a conductor. If this were a charged wire or a charged piece of copper, whatever, those charges could move around, and that's not within the realm of electrostatics. We're dealing with charged objects where the charge can't move if it's plastic. Okay. So business as usual. Probert is standing right here. Let's see. Find the electric potential at point P1. So Probert's standing right here. All right. Probert is standing, apparently when Probert stands at P2, I think we didn't deal with that because now we're dealing with non-uniform charge density. All right. So what's the charge there at point P1? Let's go about our business as usual. Let's name the differential charge element. Here it is. There's a little teeny tiny differential charge. I'm going to give this a name of dq. Its size is dx. Dx is the size. From there to there is dx. From there to there is dx. It has a location. The location of dx is x and y. So here's the origin. There's the origin. Dx is located at a distance x from the origin. Right here. Okay. X. So I've named my particle. I've specified its size. Let me just go through this. Here's the name of my particle. Here's the size of my particle. Here's the location of my particle. Probert's standing here at P1 because the question is saying, find the electric potential, find the voltage at point P1. Okay, so I don't know how to deal with these complicated objects, but I do know how to deal with the voltage due to a point. It's KQ over R equals, so I'm going to deal, that's macro, this is for a point. So I'm going to just rewrite it in this format, K dq over X. So R becomes X because technically not. R becomes L plus D. Okay. So what's the distance between my source charge, my differential, my teeny tiny source charge dq, and Probert? It's big L plus little d. Okay. So, and I'm using differentials because differential means anything that's differentially sized is point sized, and I know how to deal with points. Now let's talk about DQ. This is non-uniform. So this throws a wrench in everything. Okay. So I'm still going to go with lambda is charge per length. And if you wanted to, you could say, well, okay, charge per length is big Q over big L. But you know what? I'm not going to say that here because I actually have to say dq over dx because lambda is non-uniform. Okay, so number 3. So because it's non-uniform, I can't say the following. No matter, I can't say that a sample right here, for example, I can't say this sample right here has the same density as this right here. In fact, I know for a fact they do not have the same charge density. So I can't say that because this is non-uniform linear charge density. So I'm just going to write dq equals lambda times dx, and lambda for me is given as cx dx. Lambda is given as cx. So that's my expression for dq. So maybe this isn't such a big deal, but I'm going to update number 1. Here's update number 1. I have that differential charge, that the voltage that Probert feels due to that little teeny tiny dq is equal to K times dq cx dx all over L plus D. And I guess that's it. Can I get any more creative? And I'm just asking myself, can I peel this apart any more? Can I drill down to specify anything further in terms of geometry and material properties? Any more geometrical steps I could invoke? Any more material steps? I can't think of anything right now. So number 5 is time to integrate, I guess. The voltage at point P1, I'll read it like that, equals the integral of my differential. This is me taking a single point, the effect of a single point, and gluing them all together. So my limits of integration, I'm going to go from, I guess I better go from L plus D to D. Is that right? Because Probert is standing right here. And what I'm doing with these limits of integration with my boundary conditions, I want to say I'm taking all of these elements. So it's as if I'm taking all of these teeny tiny elements all the way out here, that one, and this would be L plus D away from Probert, and then gluing them all together like this until I get down to D. So I think that's correct. And certainly we should talk about limits of integration because a lot of times that's the tripping point. But I want to take the point all the way out at distance L plus D and go all the way to D. Okay, and the way I just double check myself, if L equals 10, and well, for me, let's see, L equals 0.16 and little d equals 0.032. Okay, that looks good. All right, times K times C times X dx all over the distance between, and I made a mistake. I gotta update my mistake. This should be what's my mistake? You guys shout it out. Where do you see my mistake made? There is a mistake. There's only 4. My mistake occurred in steps 1 through 4. Where is it? Maybe I'll just add some time. You guys need to figure out where my mistake is. While you're doing that, I'm going to open the next quiz. Chapter 24, quiz 5. Let me come back to this. 1, 2, 3, 4, 5. 5 is 37. Okay. I'm going into chapter 24, quiz 5. Chapter 24, quiz 5 should be problem 37. It is. That looks good. 1 second.
Should R be equal to L minus D?
Nope. Chapter 24, quiz 7. Well, let me get the 7, then we'll come back to this. Chapter quiz 5. Let's see, it's now about 10 a.m. Okay. Chapter 24, quiz 5 is good to go. But before we start that, let me go back to this problem. All right. Ooh. I'll give a hint. The problem, my mistake first was made in step 1. What's the problem with step 1?
Is it that you have the full length instead of X?
So what should the change? What should step 1 be?
R X K or K DQ over X plus D.
Okay, that is it. That is correct, because what is this denominator? This denominator is, I've replaced R with this denominator. Let me just make your correction. And I actually think what I'm going to do, I'm going to intentionally make a mistake in every problem, because that's obviously, if you're just following, if you're just copying down what I'm copying down, including the mistakes, that could be one of the root causes here that needs to be remedied. So this is X, as you said, Jordan. Okay, so R becomes R. What is R? R is the distance from Probert to the source charge. Okay, so KQ over R is good for a starting point, but then I substitute in, and I just need to make sure this is clear. X plus D is the distance from Probert. Here's Probert right here. The distance from Probert to this differential source charge is D plus X. So that looks good there, which means I should fix it here. X plus D. I'll fix it there. And then right here, this is X plus D. And then we're done. You guys can take it from here. Let's see. Do we know K? Yes, of course. Do we know C? C is given. PC means picocoulomb. So let's just do this checklist. I know K. I know K. I know C. Do I know D? I do. D for me is 3.2 centimeters. Good to go. Finish it. Let's come up for air and then start the next one. And again, I think that's gonna be my new resolution. Always make a mistake.
I think you made another one.
Where?
Isn't it supposed to be KCX dx? Not just D.
Yeah, that's a good catch, Matt. I think I erased the dx. K cx dx x plus d. All right, good catch. All right, let's get this answer correct and point out any other mistakes you see. That one was not intentional. Neither was the first one. But going forward, I'm all about making mistakes and all about having you guys find the mistakes. K C. We need a lookup table for this integral. I don't think so, do we? I don't think we need it. Let me just make sure it's not available. No. It's not available because I guess we don't need it. So the question is, I guess, that I would have for you guys, what's the integral? What's the solution to that integral? Let me just do number 6. Number 6, the velocity at point P1 equals K comes out, C comes out, L plus D to D of X dx over X plus D. And do we know that integral? What's the integral of X dx over X plus D? I'm just wondering if this is not given to us as an integral. I'm looking at the table. If I think I'm gonna do one other change here. Yeah, I need to make one other, I don't know if that, well, let's see. If I'm specifying this as X plus D, this is the distance. This is the distance from Probert to my source charge, then I need to change my limits of integration. Okay. I don't need to do L plus D because I'm already accounting for that D distance. So that's right. All right. Let me just recap that in case you didn't hear. The fact that I'm using this setup for the distance between Probert and my source charge DQ, X plus D, means I've already accounted for this offset. So I don't want to go from, I basically just need to capture this length of the rod. And if I do that, I don't need to go from L plus D to D because this D here already does that. So that's my thought process. So let's see. L.6 minus little d. Okay. Let's see how everyone's doing. This is quiz 4, is it? Most of you are done. Most, but not all. And this is quiz 4. Okay, so I think we're good to go. Quiz 5. Let me double check. 1, 2, 3, 4, 5. Quiz 5 should be 37. Interesting. Quiz 5 should be 37. Okay. maybe a few more moments here, waiting for people to get enough time.
Pico is to the negative 12th, right?
Correct.
Uh,
Pico. Still a good number of you needing additional time. So is there actually, so everyone's done with quiz 1, quiz 2. A few people still need to work on quiz 3. Quite a few people still need to work on quiz 4. So if it's a matter of time, that's one explanation. Or if you're stuck, we should talk about getting unstuck.
Can you change the time for quiz 3? Because it still shows it closed
Yeah,
at 3 a.m.
Quiz 3. If I check on my quiz 3, chapter 24, quiz 3. According to my instrument panel here, chapter 24, quiz 3. I can extend that, but I'll go back and I'll add that after we're done with, I guess, quiz 5. Well, or maybe I'll put that during the stop time. All right, so let me just do that now. It's chapter 24, quiz 3. Okay. All right, chapter 24, quiz 3 is now extended. Yeah,
It shows up now. Thank you.
okay. A couple more minutes. Hmm. Oh, they did give it. Maybe you guys saw it. They did give this integral. Let me put that on the screen. In the handout that you will receive, the table includes the integral we're dealing with. So right here, I'll paste it right here. This is from the table. So when you get an integral in this form right here, you would either know how to do this using integration techniques, or you would just look it up. Another option is to do it on your calculator. The only problem with doing it on your calculator is it might eliminate some partial credit opportunity if you get the wrong answer. But in general, either way is good. Look it up at the table, do it on your calculator. Okay, so that was integral number 21. Let's move on to the next quiz. This is shifting gears. In your green sheets, in the green sheet lecture video, there's this whole section here called how to get the voltage from the electric field. Calculating the voltage from the field. So this is the section I'm referring to, covered in detail in the lecture video. And let me just, there. Okay. How to calculate the voltage from the field. Voltage due to a point charge. I guess that's it. Let me check here. Calculating the field from the voltage. This problem is, all right, so we're calculating, this is calculating the field from a voltage. So this problem says, what is the magnitude of the electric field at a certain point if the electric potential is known, if the voltage is known? All right, so let's just start with a drawing. This is a three-dimensional situation. So here's the three-dimensional coordinate system. And this problem is saying Probert is standing at a certain location. They tell you where Probert is standing. Probert is standing 9 meters over here and negative 1.3 meters here. And then coming out of the screen, 9 meters. Probert's standing right there. Basically, based on the givens in your problem, you know exactly where Probert's standing, and specifically, let me just be careful here. This is, for my problem, this says 9.10 I hat meters. So you go in the plus X direction, 9.10 I hat meters. You go south in the negative Y direction, negative 1.30 J hat meters. And then you come out of the screen in the positive K hat direction, which is the Z direction, another 9 meters. So this would be 9.00 K hat meters. You should indicate that X and Y are always perpendicular and Y and Z are perpendicular, or I should say the X plane, the XY plane and Z is perpendicular. So I always just add these little indicators to try to give some three-dimensional appearance. But this is where Probert is standing. Probert is standing exactly at this point in three-dimensional space. And we know what's going on with voltage. So we know, in my case, number one, voltage equals 6.80 X, Y, Z squared. So you know what we can say right away? We can say, aha, voltage is a function of space. Voltage is a function of where you are is a function of space according to this function. So very non-uniform. So it turns out because we know the linkage between voltage and the electric field, we can reverse engineer it. So number 2, let's reverse engineer to find the electric field at point P. Which is where Probert is standing. So specifically, how are we going to reverse engineer it? According to our lecture notes, this is what we're dealing with. We're dealing with Probert standing at a certain point. So if we go through, so what we're doing here, we're starting with the definition of voltage. We remember the relationship between energy and work, and you can see, so as we go from steps 1 through step 6, if we go from steps 1 to step 6, we can actually find the relationship between the electric field and the voltage. So I'm just going to take a little snip of this. Okay. And apply it. Box number 6 was prefaced with just some basic steps. Really all we did is the definition of voltage along with, and that's pretty much it with work. Okay, so this is what we need to apply. We need to apply this relationship right here. Okay, so let's do this. And all this is saying is that it depends. It depends on what way we're looking. So I can say that according to this relationship between voltage and electric field, the electric field in the x dimension is equal to negative partial derivative of V for voltage over partial derivative of X. So you might not have ever heard of partial derivatives before, but you did because you watched the green sheet lecture video. And I'll jumpstart things here as well. Basically, here's the electric field in the X direction. It's going to be minus partial.
Can't see the problem.
Minus partial with respect to X of my voltage function, which is 6.80 XY Z squared. Okay. And let me backtrack here. This is my voltage. Where does this come from? You engineer, you as a designer, you as a scientist or an engineer, design a system that produces this voltage phenomena. And there's many ways to do this, but you provide this voltage situation. It depends on X, Y, and Z squared. Voltage is a function of space according to this function. So, okay, where you stand determines the voltage you're subjected to. Let's reverse engineer to find the electric field at point P. And that's what boxes 1 through 6 from the lecture video and your green sheets have produced these relationships. So I'm just saying in step 3, okay, let's do this dimension by dimension. Let's just deal with X, and then we'll deal with Y, and then we'll deal with Z. But here's the X component of the electric field at point P. It equals minus partial with respect to X. So this is going to equal 6.80. So it's just like a derivative. You're going to treat this, you're going to do number 3 exactly as if it were just a regular garden variety derivative. except you're going to consider y to be a constant and z squared to be a constant. So it's just a very simple derivative in step 3. So what are the constants in this expression? 6.80 is a constant, and y z squared is a constant as well. So we're just left with, and I can't forget that negative sign. What is the partial of what's not constant with respect to x? Okay. And this answer is negative 6.80 y z squared, evaluated at y equals negative 1.3 meters and at z equals 9.0 meters. And let me just go back and repeat kind of what I just said for reinforcement purposes. I know if you guys saw this would be a no-brainer. Negative derivative of voltage with respect to x. So we're not using this expression. We're using partial derivatives, not regular old derivatives that you're used to. And when you take a partial derivative, it means you take everything as a constant except for this variable. All right. So if I look at number 3, I'm taking negative partial v with respect to x, which means negative partial v with respect to x of this voltage function, which is right here. And in the case of partial derivatives, we're basically just saying, hey, all I care about is how things are changing with respect to x. So if all I care about is how things are changing with respect to x, this is considered a constant and this is considered a constant. And that's how I go from step 3 to step 4. Negative 6.8, negative 6.8 is a constant, y is a constant, z squared is a constant. So I'm left with partial of x with respect to x, which equals 1. It's like saying, what is dx over dx? It's just the numerator equals the denominator. So that's how I ended up with my expression in step 4. Because all I'm caring about is what Probert is feeling in the x dimension. And specifically, Probert is standing at these coordinates. So I'm plugging in my y value because that's where that's Probert's y location at negative 1.3. And I'm plugging in the z value because that's Probert's z coordinate. So the upshot is step number 5. The electric field in the x dimension is negative 6.80 times negative 1.3 times 9 squared, or 716.04. Let me double check that. 716.04 volts per meter.
Can you scroll down, please?
Yep. Okay, and I'm just going to double check that. Negative 6.8 times negative 1.3 times z squared. Okay. I'm getting this. Notice the units. A volt per meter is equivalent to a Newton per Coulomb, and this was shown in the lecture video. And even if you didn't catch that part, you can just look at this expression right here. If I did the dimensional analysis just on what you see in step 3, my numerator is volts, my denominator is meters. All right, so I have the answer. I know what the electric field is in the x dimension at that particular point where Probert is standing. Let's do the exact same thing for y and z. So number 6, EY, the electric field in the y dimension, same thing. Let's take the derivative of my voltage function with respect to y, but it's not regular derivatives, it's partial derivatives, which means negative partial with respect to y of my voltage function. My voltage function is still 6.80 xy z squared. And in the case of partial derivatives, I'm saying, hey, I don't care what's changing in the x dimension or in the z dimension. I only care about what's changing in the y dimension. So in this context, 6.80 is a constant value. Z squared is a constant value. And x is a constant value. So this is what my integral looks like now. Step 7, EY equals negative 6.80. X is considered a constant. And again, in reality, it's not a constant, but we're ignoring it. We're just isolating what's happening within the realm of the y dimension. Z squared is a dimension. And so I'm left with the partial derivative of y. So once again, this is not heavy lifting in terms of the actual differential derivative we have to deal with. This equals negative 6.80 x z squared at x equals, where's Probert standing? Probert has an x coordinate of 9.10 meters, and Probert is standing at z equals 9 meters. Right, 9.0 meters. Okay, so step 8, here's the y contribution. Here's the magnitude of the electric field in the y dimension. Negative 6.8 times 9.1 times 9 squared. Negative 5,012.28 volts per meter J hat. And over here, I should have put I hat. I need to specify I hat is saying this is the direction in the along the x-axis. This is the magnitude of the electric field along the y-axis, and I just want to double check this. Negative 6.8 times 9.1 times 9 squared. Okay. Last but not least, EZ. Same conversation. All I need to do is figure out how is my voltage changing as a function of Z. So I'm going to do negative partial with respect to Z of the same voltage function, 6.80 x, y, z squared. Partial derivatives means I don't care about anything except for the z dimension. 6.80 is a constant, x is a constant, and y is a constant. So if I bring my constants out of the derivative, I have EZ equals negative 6.80 times x times y partial of z squared with respect to z. And I have my expression that I can plug into. EZ equals negative 6.80 x times y times 2z, because the partial derivative of z squared, just like a regular old derivative, is just going to equal 2z. So this is the big, I mean, it's still simple, but this is a little bit different because z was raised to a power of 2. And then you're just going to evaluate this at y or x at the coordinates. This needs to be evaluated at x equals 9.1 meters y equals negative 1.3 meters, and z equals 9.0 meters. And we're going to get an expression for EZ to go along with EX and EY. Okay. And I did, yeah, okay. Negative 6.8. Fulton 47. Volts per meter in the K hat direction. Double check that. All right, I'm getting the same answer twice. So, oh, and I'm seeing a mistake. Did anyone spot my mistake here? This is not a catastrophic mistake. It's just a notation mistake. There's a mistake here. Because I don't want to take too much time, doing an Easter egg hunt. Although there's something about that appeals to me. I'll just fix it. This belonged up here. Okay. All right. So I have all three vectors, and I should indicate EX is a vector. Okay, so let's see. I have my EX vector. I know what's going on from an electric field point of view in the X dimension. So this is EX is a vector. Electric field is a vector, magnitude and direction. EY, that's also a vector. And EZ, that's also a vector. So I have my three components. This is my X component right here, going in the positive X direction. Here's my Y component of my electric field that's going in the negative Y direction. And here's my Z component of the electric field. It's going in the positive Z direction. The problem asks, though, what's the magnitude? So they're not going to care about the net direction. They're only going to care about the magnitude. So I just have to do Pythagorean theorem. If I just do a little auxiliary coordinate system here. All right, this is what I ended up with. Here's my X component. My X component is 716 and some change. That's my X component. My Y component is going in the negative direction. And my Y component is going in the negative X direction. Let me try that again. Oh, wrong geometry. Okay, and what's going on with my Z? My Z is coming out of the screen like this a little bit. Okay. So this is what I just figured out for E sub X. That's my E sub X. This is my E sub Y. This is my E subscript Z. So here's my net electric field at point P. So once again, Probert is standing right here. So that's why I have multiple coordinate systems. Probert is standing right here. And at this particular location, Probert is feeling a net electric field that looks like this. And this is Pythagorean theorem or distance formula. That's perpendicular, that's perpendicular. So I can say the net electric field using Pythagorean theorem, E, which is right here, E, at that point that probert is occupying is just going to equal EX squared plus EY squared plus EZ squared square root. Okay, and we have all of these values stored in the calculator, although I don't think I stored mine, I should have. But let's use Pythagorean theorem. Okay. 52.26 and some change. That's the answer. That's the answer. We've reversed engineered the voltage behavior to figure out the electric field that exists at this particular point. Just saying that multiple times because that's the moral of the story. All right, so let's see. 1044. Let's do this. 1044. 1051. See you at 10:51 a.m. One more for today. One more, chapter 24, quiz 6. Let me double check my side. Chapter 24, quiz 6 should be homework problem 2456. Okay. And this is a potential energy problem. Let me get rid of this clutter. All right. So in many ways, this is like the other. Well, there's 2456. This, oh, I didn't want that one. Okay. 24.56. This is a potential energy problem. I think at the beginning of today, I basically said there's just a couple of basic categories in chapter 24. Let me repeat that just because I think it's useful to keep things in perspective. Otherwise, sometimes you can't help but think there's an infinite number of weird situations you have to deal with. And that's never the case. There's a very finite number of situations you have to be familiar with. And specifically, this is the voltage. You need to be adept in figuring out the voltage due to a point charge, multiple point charges, a line or arc of charge, a surface, a charged surface. Talked about that. I think we did problems in all of these areas. And then I should have inserted, we need how to get E from V and V from E. And then really the third category is energy, potential energy, electrostatic potential energy. I'll just put potential energy. I'm going to write potential energy because this is another kind of potential energy we've dealt with. Potential energy. So if I make a little list of the potential energies that have officially been covered in the first physics course and the second physics course, we had gravitational potential energy. Maybe that's a familiar term. We had elastic potential energy, like springs energies. And this is the third kind, electrostatic potential energy. And then we'll get into pretty soon, magnetic potential energy, and so on and so forth. But right now, this is the third kind of potential energy that we're dealing with. And in your green sheets, this was the last section. A system, the electric potential energy of a system of particles. So it once again starts with the definition of voltage and basically just says, okay, well, I know what energy is. I know what voltage is. And maybe I'll just take a snip of this. Maybe I'll take this. Okay. So this is the electrostatic potential energy due to a bunch of charges. So I'll keep that over here for reference. All right. So we have to do some graphical interpretation. All right. We have a graph and a figure. We have two graphs, really. Particle 1 has a positive charge. So particle 1 will make a positive energy contribution. Particle 2 also has a positive charge, are fixed in place with a separation of little d. Particle 3 is movable. So particle 3 can move along the x-axis to the right of particle 2. This graph right here gives the electric potential energy. And you could say the potential to do what? That's always the first question that pops into my head. When you use the term potential energy, potential to do what? And the answer is the potential to do work. So this electrostatic potential energy as a function of X of Q3. So I just want to make sure I'm keeping my head screwed on straight. This is location of Q3. This is the location of charge 3. Charge 3 is movable. So this is a graph of system. This is total potential energy of the system. There's 3 charges in the system. The total potential energy of the system versus the location of charge Q3. This is the graph we're looking at. And just instinctively, you do standard graphical analysis. What does anything, and when I say that, look at the x-intercept, look at the y-intercept. So this is just a standard list of considerations to keep in mind when you look at a graph. Anything noteworthy about the x-intercept or y-intercept? What about an inflection point? That's probably a good thing to think about. What about a max or min point? So it's, again, this is the standard list of considerations that should just start coming to mind right away whenever you do graphical analysis. What about the slope? What about the area under the curve? And maybe a few other things, but this is probably a pretty good list. And with the other thing I'll say, any crispy intersections, any easy to identify intersections. Maybe the last thing I'll do, asymptote, and I bet this is a pretty complete list, asymptotes. Okay, so we have a few of those right now. I can't help but notice right away that this point right here, that is a crispy intersection point, and it's also the y=0 point. So that is certainly noteworthy to me, right at that point. And then it actually says, does it talk about an asymptote? Particle 3 can be moved along the x-axis. We have a potential energy of the 3-particle system as a function of the x, the scale of the vertical axis. Okay. So I don't know. They don't say this is an asymptote, but it kind of looks like one. So just so I don't forget about it, I'm just going to draw an asymptote here, but I don't think there's going to be anything I can really do with that because they don't give me that value, but we'll see. We'll see. It just caught my eye. All right, so number one, for three particles, for these three particles, the total system potential energy, and again, potential to do what? And the answer is the potential to do work. The total system potential energy is U equals, I guess I just can copy and paste this. U equals, this is what this is saying. This is saying U equals the potential energy between 1 and 3 plus the potential energy between 1 and 2 plus the potential energy between 2. And let me back off and maybe go in order. So if I just do superposition, I'm going to say, hey, the total potential energy is whatever I have between particles 1 and 2 plus whatever potential energy exists between particles 2 and 3 plus whatever potential energies exist between 1 and 3. All right, and again, this is a superposition type of approach, which means let's just chunk things up into small bits and then combine them to get the aggregate or macroscopic value. All right, and so before I go on, because this is kind of an easy problem to do, but what is the potential energy between these two charges? Well, let's see. They both have a positive charge. So the potential to do what? The potential to do work. If I suddenly let go of particle 1 and particle 2, they would go flying off in opposite directions because they both have a positive charge. So they would have all of this kinetic energy. As soon as I let go of particle 1 and particle 2, that potential energy is used to create all this kinetic energy because particle 1 hates particle 2. So that's my interpretation of potential energy between 1 and 2. Particle 3, well, that's also positively charged. So it's the same conversation. It's the potential energy that would get spent on producing kinetic energy because all of these particles would flee from each other. All right, so number 2. This potential energy is going to equal the potential energy between 1 and 2. Again, I'm going to focus on 1 and 2 is just going to equal K Q1 times Q2 all over R12. Okay, so just so you're not confused, we have these all kind of start to look the same. We had F equals K Q1 Q2 all over R12 squared. Fine. We had the electric field equals K Q1 all over R1 squared. Then we had voltage for a point equals KQ over R. And as if that's not enough, now we have potential energy is K Q1 Q2 all over R12. So look at how your head could be spinning. Look how similar these all look. And one thing that will help you keep your sanity is if you can actually relive the derivation of these. Otherwise, you're just going to have to hopefully look up equations and hopefully you're looking them up the right way, and which is fine. I get doing that, but here's my point. Look how similar these all look to each other, but they're profoundly different and yet related. All of these are, here's the good news. They really are all related. These are all part of the same family, which I guess explains why they kind of look pretty darn similar. But I just wanted to throw that out there because that could be confusing. I would understand how that's confusing. So what's the potential energy between particle 2 and 3? It's K, follow the subscripts, Q2, Q3 over R2, 3. And last but not least, so I dealt I've dealt with this term, this term. Now it's time for the potential energy between 1 and 3. Follow the subscripts K, Q1, Q3, all over R1, 3. And then that's it. So number 3, the potential energy. Okay, maybe I'll do, what's R12? R12 is the distance between particle 1 and particle 2. Just follow the subscripts. The distance between particle 1 and particle 2 is, for me, 0.04 meters. So I can just say this is going to be 0.04 meters. What's the distance between 2 and 3? That's variable. But you know what? I'm gonna do this. I'm gonna drive a stake in the ground. I'm going to look precisely at, let's look at X. Let's look at the X location. When the location of particle 3 is at 0.10 meters, I know one thing, U equals 0. Okay, so is that right? Because when particle 3 is at this 10 centimeter mark, which is 0.1 meters, according to my graph, there's no potential energy. And let's think that through before we just blindly follow orders. That's basically saying, well, I have Q1 is going to be repelled by Q2 and 3, but Q2 is going to be, so we have all of this mutual repulsion. But if you play your cards just right, if I move Q3 exactly to X equals 0.1 meters, then everything offsets. That everything just balances out. All of the repulsion and all of the attraction perfectly counteract each other, which is why there's no potential energy. It means if I let go of all 3 of these particles, they would just, they would stay where they are, which would be kind of a neat thing to see. All right, so I'm driving my stake in the ground at the position of particle 3 being precisely located at X equals 0.1 meters. So then number 4 says, okay, I have 0 equals K Q1. I guess I'll start plugging in numbers here. What's K Q1? Q1 is 5 microcoulombs, positive 5 microcoulombs, positive 5 microcoulombs. Q2 is 3 microcoulombs, positive 3 microcoulombs, over the distance between 1 and 2, which, as mentioned, is 4 centimeters or 0.04 meters, plus K Q2, which was 3e minus 6, times Q3. Q3 is I don't know, and I guess that's the dollar sign. So I don't know what Q3 is. Just leave it as Q3. What's the distance between charge 2 and charge 3? Where, well, at this particular moment, their distance is 0.1 meters. Because when that distance is when Q3 is sitting at X equals 0.1 meters, I have 0 potential energy. And then what about Q1 and Q3? It's K Q1, which is 5e minus 6. And this should be coulombs squared, and this should be coulombs. All right. Q3, what's the value of Q1, Q3? I don't know. It's still Q3. What's the distance between 1 and 3? The distance between 1 and 3 is going to equal 0.14. 0.14 meters, because let's be careful. The distance between 1 and 3 is right here. All right. The distance between 1 and 3 is this. This is R13, R13. This distance for me is 0.04. And this distance for me at this particular location is 0.1. So that's how I get 0.14. Okay. So we need to solve for Q3. Yep. Okay. Number 5. Well, I can divide through by K. So the K's cancel. K, meters cancel. So I'm left with this. Well, at this point, solve for Q3. Can I solve for Q3? Let's try to solve for Q3. So that's the magical value of Q3. If Q3 had that value, all of these the system potential energy would actually be 0. No potential. There'd be no potential for anything to move. No potential for kinetic energy. So there, let's see time. It's a good time to stop, actually. That's 6 quizzes. This seemed like an extra grueling day. Maybe it's because I was not very sharp and making a few unintended mistakes that were costly. Well, almost. They're all fixed now, I guess. But all right, let's see. 6 quizzes now are all done. Your exam is on Thursday. Your traffic light report deadline is tomorrow at, let me double check that. Tomorrow at 10 p.m., I think, if I just want to double check. Here's your traffic light report. Where I want to go back to chapter 24 because it's been a while. It's been a while since we hammered on chapter 24, at least together as a class. Maybe, hopefully you've been cycling through chapter 24 and revisiting it multiple times via your traffic light report. That really would make a difference. Otherwise, I mean, I've been in the situations, well, by the time the exam rolls around, I haven't seen chapter 24 in ages and I've grown stale, and that's not good. So I want to go back to chapter 24, this is a homework problem. And just what are you going to see on Thursday? You're just going to see homework problems. You're just going to see a setup. You're going to see problems that are very consistent with the homework. You're going to see a mesh method. Let me repeat again. You absolutely have to do your mesh method spreadsheet in Excel. So if you're doing, if you're getting if you're getting your Excel spreadsheet set up and you say, I don't know how to do matrix multiplication in Excel. I've done it in Google Sheets, or I don't know how to do min versus in Excel, or how do I do this? Again, you can't let that happen. You have to have all of that Excel mastery digested. Okay, so I just wanted to cover those critical points. It's now time to do chapter 24, quiz 8. Let me see. 1 second. I think I put it in the wrong area. I have to go searching for chapter 24, quiz 8, which is, oh yeah, and I'm seeing it, but you're not. Chapter 24, quiz 8. So give me a moment. It's not in 57. I think I just have to create. So this will take a minute. So as I do this, chat amongst yourselves. I want to go back to chapter 24 and revisit this problem because it's a good potential difference, a good voltage problem. Remember, voltage means the same as potential difference means the same as potential. I try to use the term voltage. And this uses a standard calculus approach. And last time I remember, like for electric fields, some of you didn't even do the setup correctly, or didn't I shouldn't say that. Some of you didn't even offer a basic setup. And that is low-hanging fruit in terms of points. So pay attention to methodology, pay attention to the recipes, because at the very least, you're going to get a substantial amount of points if you can just set it up the way I've been doing, very repetitively in this class. All right, so 1 second. Chapter 24, problem 40, which I think this is a double dot problem. Thirty more seconds. Okay, I think it's there now. So refresh. Chapter 24, quiz 8 should be available to you. And it should look like the screen that I'm sharing. Chapter 24, quiz 8. Okay. So this was a homework problem, but this is the rare homework problem that didn't have an associated deep dive and didn't have and I didn't cover via a quiz, which again, between the deep dives and what we do on Tuesdays, pretty much every homework problem is covered. And again, that's just for starters. So you should say, okay, well, that gets me started, but that in no way is sufficient in terms of the time I have to spend to master the solution. Thin plastic rod. Plastic is important to measure. Plastic means non-conductor. So a non-conductor can still be charged. We've seen that when you were charging the pieces of tape. Remember, you had the charging paddles and they weren't working very well. So then we sort of fell back to using strips of Scotch tape. And all of those materials are non-conductors, but you can charge them. And if they're non-conductors, the charges are kind of fixed in place. You can charge it, but the charges don't move around. Non-conductor. Now, this is always fun. Always fun to see non-uniform. Always fun to see the word non-uniform, because when you see non-uniform, this isn't a 100% always true statement, but I'm thinking one thing, calculus. And I'm thinking calculus anyway, because by this point, you should know that, yeah, this is going to be a calculus situation. This is a continuously charged object. It's not a point. Points are easy. It's a continuously charged object. So right away, that tells you calculus. And non-uniform means calculus. So I guess I need to stress this multiple times, because on the last exam, there was also a non-uniform situation. Some of you picked up on that. Some of you just it didn't register. You didn't acknowledge the fact that it was non-uniform, which was kind of surprising to me, because the problem I'm referring to from exam 2 was, I would argue, almost identical to 2 homework problems, or almost a complete copy and paste from 2 homework problems. So don't let that stuff slide by you. Don't let any of this stuff slide by you. So I'm going to do the calculus thing. We need to find the voltage at point P. Probert, we hire Probert. Probert has been hired to stand right here at P2, right there. Probert's standing at P2, And Probert for part A needs to tell us what the voltage is. So this is the methodology. This is the calculus-based physics methodology that should look pretty darn familiar to you. This is like literally, I've taken you through this a dozen times. I would maybe more, I think, but many, many times. You're going to do this. And this methodology is in your green sheet. So I don't recommend this, but even if you were completely ignoring me right now and you just did the unthinkable, you just rifled through your green sheets on the exam, you still could probably get a pretty good start here. Having said that, though, if you're spending now, where was I before I was so rudely interrupted? I think I was basically repeating myself. It's a big part of learning and teaching is raw repetition. I know for a point charge, this is the expression for a point charge because I've lived through the derivation and watched the videos and et cetera, et cetera. I don't have a point charge. I have a bunch of point charges. So I'm going to differentialize. I'm going to differentialize the situation here. Let me actually take a better picture of this. So I want to be really deliberate, you guys. The methodology is important. Yeah, you got to get the right answer, but you're going to get the right answer. It's more likely you're going to get the right answer if you kind of use best practices. And what I'm going through now is a best practice. This is best practice for using calculus in physics and engineering. And I just got to find a better picture here. There it is. Okay. Okay. So I'm going to do what we've done many times before. And I'm going to do what you needed to do on exam 2. And there's a chance you might need to do on exam 3. Pay attention to methodology, to the strategic and tactical approach. I know how to deal with a point. So step 1, if this were an exam problem, I would basically identify a sample element. This sample element right here is DQ. DQ means a super teeny tiny element. It's so small, it's infinitesimally small. It's a differential element of this rod. Hence, I can consider it a point. DQ can be considered a point. So if this were exam 3, you would be drawing exactly what I'm drawing. If you solve this problem or a similar problem on exam 3, pay attention to details. The size of this point element is dx because it's lying along this x-axis. Maybe I would call it dy if it was lying across the y-axis, or dr if it was an arc element. But here, dx seems to be the best name because it's lying along the x-axis. So my point has a name. It's dq. It's point sized. It has a size. It has a location. Here's the location of the sample element. Where is it? It's x. It's x away. It's at a location x because this is the origin. This is 0, 0. Okay, so there's my whole calculus. Well, that's not my whole calculus setup. How far away is Probert? Probert, once again, is standing right here. Probert stands at point 2 right here. How far away is Probert from my point charge? Here's how far away Probert is from the point charge. Right here. There's the distance. Okay. That's the distance between Probert and the source charge. So if I were just pretending this was the only charge element that I had to deal with, I have R. There's R, the distance between the point I care about, which is where Probert is standing, and the source charge location. And I have Q. Q is whatever the charge of that element is. But I don't have just one sample. I don't have one charge. I have multiple charges. I have all of these DQs. So for example, here's a DQ, here's a DQ, here's a DQ, so on and so forth. So I'm just going to add up all of those DQs. So that's why I'm going through all the setup now. Let me repeat this. This is important. None of this, you should look at none of this as being optional. On exam 3, you kind of have to provide this. It's a methods class in addition to just getting the right answer. All right, so let's do step 2. The differential version of this, since I'm living in the realm of calculus, I would say that the voltage at point P2 is going to be the integral of dv. So I'm going to differentialize, and so I'm going to say the integral of k dq over r, where this is r. The distance between the source charge and probert is r. Okay. And then I'm going to do sort of standard operating procedure, because remember, your ultimate guiding light, the ultimate light at the end of the tunnel, is you're capturing material and geometric properties. So how can I best capture the geometry, and how can I best capture the material properties? That's the guiding hand, material properties. Okay, so here's the geometry. Everything you see in this visual, this is geometry. This is me capturing the geometry. Step number 3, I guess I'm over here. Step number 3, how do I capture some material properties? I'm going to say, let lambda be defined as charge per length. You've seen this before. You're seeing it again. Charge per length. Charge per length, I could write macroscopically, it's the total charge on that rod, that thin plastic rod, over the total length of that thin plastic rod. Microscopically, also known as differentially, I could just say it's dq over dx. Okay, and obviously this is what I'm after. I'm going to bark up this tree, because this is my differential form. I might end up needing this or using this, I don't know, but I am for sure thinking, well, this is catching my eye, because I need to deal in the differential realm, then glue all of these little dq's together. So I can say dq is going to equal lambda dx. And you've seen this before. This should look very familiar to you, this whole approach we're taking here. But there's one thing that's different: non-uniform. So this should make, as soon as you see non-uniform, among all of the other thoughts that are streaming through your head, you're thinking, I was thinking calculus anyway, but now I'm thinking even more. Now not only am I thinking calculus because I have a continuously charged object, but now I'm thinking even deeper calculus. And this is why, because it's non-uniform density. Okay, so because lambda equals cx, so lambda is c times x dx. So this is the expression I have for dq. So it's not just a constant, it varies. My charge density is a function of where the dq is along this rod, right? So let's update our differential. And as long as I'm here, number 4. All right, so the voltage at point P is the integral of dV is the integral of, and now I guess I'm returning my attention back here, K dq over R. All right, so here's K, here's dq, cx dx. Here's the distance between a given differential element, in this case dq, and probert P2, Pythagorean theorem, square root of d squared plus x squared, because Pythagorean theorem right here. I'm focused on this triangle right here. D squared plus x squared right here. D squared plus x squared equals r squared. So that's why I'm taking this square root of that. Okay. All right. And this is me. So right here, you know what I've done? I have captured geometry and material properties. That C, where's my material property? It's right here. There's where my material property lives, and everything else is geometry. And not only did I capture, but I captured it in an integral that's maybe solvable. And if it's not solvable, you just keep hammering on it. So I'm going to try to do, I'm going to look this up. Hopefully this is a lookup. I would give you a table of mathematical formulas like you see here. This is directly from your textbook. You have access to this exact same resource, which again, I would just give to you on exam 3. Do any of these, I'm not seeing, I'm not seeing our integral. So if you're not seeing your integral here, you know what it means. It means that your prerequisite skills are going to be enough. That's what it means. So number 5, I'll use U substitution. Number 5, let U equals D squared plus X squared, which means DU equals 2x dx. So now my integral becomes, here's my integral. The integral of, I'll just write it like this. The voltage at point P is the integral of KC 1/2 du all over U to the 1/2. So just, we're living in integral calculus land, sort of garden variety. Again, stuff, I think that's a true statement. If you don't find this integral in your lookup table, it's because your prerequisite skills are sufficient. So this is going to, if I take out all of the constants I have, and keep your eye out, certainly feel free to chime in and tell me when I'm making a mistake. 1/2 K times C integral of U to the minus 1/2 du equals 1/2 KC, 1/2 KC U to the 1/2 all over 1/2. All right, so U substitution says that this voltage potential difference at point P2 is going to equal the integral. I forgot the integral. No, I did. Equals KC U to the 1/2 KC times U, which was D squared plus X squared to the 1/2. And then my limits of integration, I'm going to take this DQ right here at the extreme ends. I'm going to take that DQ and all of the intermediate DQ. So I'm going to go all the way out to L and glue them all together between L and 0. That's what these limits of integration are telling me. So L to 0. All right. Is this right then? Did I KC? I suppose that's correct. So let's get a voltage value. Well, you know what? I'm going to do one step because I'm going to need this for part. I'm going to stick with this for a bit longer. Equals KC times D squared plus L squared to the 1/2 minus, if X is 0, it's D squared to the 1/2 minus D. Okay. Do I know D? Let me fix this. I think at this point, I know all of these variables. Do I know D? D is right here. D is given as, yeah, I do know D. Do I know L? I do know L. Do I know C? Yeah, pico. Pico is 10 to the minus 12. So let's get the right answer to part A and then move on to part B. (68) E minus 12. All right. 0745. Done with part A. Let's see how everyone's doing. Okay. No one's, well, no, a few people are doing part A. Should wait a bit. This is the time, guys, especially those of you who aren't happy with your exam 1 and exam 2 scores. If you're getting the right answer, you should still be asking questions. If you're not getting the right answer, you should be asking questions. Silence is not a good ally in this case. It hasn't worked for you thus far on exam. And I'm talking just to anyone who's not happy with your exam 1 or exam 2 score. So I don't want to rush. I'll stand by. Feel free, you guys. If you need some time, great. I know some of you are stuck. I just do. I do. It's not like I'm a mind reader, but you should just speak up and say, hey, where, you should ask me, like, give me your numbers and let me crunch with your numbers, and then I can troubleshoot that way. So available for Lifeline support, whether it's just me using my equation with your numbers or talking about something deeper than that. So I think Ron, Elgert, Roman, Matt, Dan, Luke, Steve, you're good to go. And then I think everyone else needs a bit more time, which is fine. No reason to go too fast. On one hand. On the other hand, at some point, you got to reach out.
I had a question.
Yes.
So, like, I got the right answer, but
Yeah.
when I do use like say I'm using for scientific notation, I just put like E negative something, or like for that, I always get the wrong answer. But when I put like the number times 10 to whatever exponent, it always gives me the right answer. Is there a reason for that?
I don't know. I would have guessed. My impression was that in Wiley Plus, you can use E to the minus whatever.
Because when I did like this problem with like the E notation, I got 4.38 E negative 20. But when I did it with like a times 10 to the negative, like whatever exponent, I got the right answer, which is 0.0438.
Right.
volts.
What do you mean E negative 20?
So I'll just show you.
The approach you see here on this screen, it's there for a reason. This is considered a best practice. This is what you as a potential scientist or engineer or technologist, you should be waking up every morning saying, and just like look at this sky and say, I love methods. I love methodology. So I know I do. And then I pet my cats. So you guys got to kind of embrace this approach. And if you did, worst cases, you're just going to do okay on the exam. Best cases, you're going to do really well. So that's the goal. That's the goal. All right. So now, but part B, what's the electric field? What's the electric field? So this is what makes this problem really good. And don't, when I say stuff like that, when I say like, this is a really good problem because it's, there's a lot of diversity in this problem. Don't let yourself think, oh, well, then this means it's probably going to be on exam 3. I mean, it's really a random process, you guys. I really just sort of like throw darts at a dartboard in terms of what topics I select. And then once I figure out the topics, I just go into the homework and recycle the homework. So your job is not to try to be strategically clever in terms of cherry picking what problems might be on the exam. Your job is to know everything in the homework assignments, whether there's a deep dive or not, whether I covered it via a quiz or not. So number 9, step 9 says, to find the electric field at point P2, I will once again use E, the electric field. They want E sub Y. So they actually said E sub Y. To find E sub Y, I'll use E sub Y equals negative partial V partial Y. So we're seeing this expression a number of times. And it's just because of utility. It's not because it's more fun. But this links voltage and electric field. This is the linkage. This is a linkage between voltage and electric field. In fact, this is how I find the electric field from voltage gradient. This expression here, it's actually termed a gradient, voltage gradient. Gradient just means a slope, or how things change as a function of space or time. This is a voltage gradient. So it's just a fancy term. Voltage gradient is change in voltage over change in Y. So seen this many times before, and this is the tree I'm going to bark up, because all I need to do is take the partial derivative. All I need to do is take dv dy, and I have v here. However, there's a little bit of prep I need to go into this. Number 10. Here's my voltage equation. Here's my voltage expression, which I had to do some heavy lifting to get to that point. Here's my voltage expression with, now what I'm going to do with D becoming Y, because it says, now that I know the voltage at this point right here, I know the voltage at this point. Now I want to go on a tour. I want to ask myself, well, how does my voltage change? How does my voltage change as a function of this Y position? So right here, this is my Y variable right here. Okay, so this purple line, this is my Y variable. So again, I'm saying, well, D, I consider D as basically just a constant for part A. Now I'm going to make D a variable. D is my Y variable because I need to figure out what the electric field is in the Y direction. So you should know, and this is where another little nudge, you guys. By this point, you should know that, of course, you're going to draw electric field lines, which kind of is something I should have done ahead of time, but I didn't really need to, but I do need to now. So here are all of the little electric field lines squirting out of this differential charge. There's one, there's one. There's an infinite number of these electric field lines emanating outward in every direction. I don't care about any of them except for this one right here, because this is the electric field line that actually is encountering Point P. Point P encounters that electric field line. Let me change colors right here. Okay, so right there, that's the electric field line that I care about. In fact, maybe I'll move it because you should also know by now, you should know that you draw the electric field line initiating at the point or terminating at the point. Yeah, you can draw all of these sample electric field lines, and you should, but you should also draw the one electric field line that you care about, which is the one that's encountered by Probert, and that's right here, which I'll just call, this is differential E. This is differential E. This would be the X component, which I'm not asked to investigate. And this would be the Y component, which I am asked to investigate. So even right now, I know one thing. Whatever the number is, the direction is plus Y. So that's just a good sanity check. This would be DEY. This would be DEX. And I don't care about DEX. Okay. So you could actually try to go back and do what we've done before, but you'd fail. Well, I shouldn't say I won't say you're going to fail. All I'm going to say is we've solved this problem before under maybe a different set of circumstances, but whatever we did before, what we can do now is just take the derivative. We can take the derivative of my voltage expression. Here's my voltage expression. My voltage, and I'm looking here. My voltage expression is going to be voltage equals KC bracket Y squared plus L squared. Y squared plus L squared to the 1/2 minus Y. So what you see here, this expression is identical to this expression, except instead of using the constant D, I'm letting D become Y because I need to basically figure out how voltage is changing as a function of Y. That's why I'm doing this. I should say this. Here's my voltage expression with D becoming Y because I need to know how voltage is changing with respect to Y. I need to know how this voltage, which I've already figured out, changes as a function of Y. Okay, that's my motivation here. So now I just have to take the derivative of number 10. So number 11, E subscript Y is negative partial with respect to Y. So it's just take the derivative with respect to Y, which means you just ignore everything else. Is just ignored. Any other variable, which there are no other variables, but any other variable gets ignored. Or I'm sorry, any other variable would be considered a constant. So what is the derivative of KC Y squared plus L squared to the 1/2 minus Y? Okay, so I know how to do that. This is power rule. So E sub Y equals negative KC. I can pull that out. Negative KC. All right, 1/2 Y squared plus L squared to the negative 1/2 times 2Y right, I suppose, minus 1. And let me double check that. KC comes out of the integrand. No, KC comes out of my differential. Negative KC 1/2 Y squared plus L squared 2Y. Okay, that's good. So then, I mean, if that's correct, then I would plug in at Y equals at Y equals D dot dot dot. I get something. E sub Y. Okay. So now we can evaluate. 9.00389. Newtons per coulomb, although in this case, it probably would be volts per meter. Volts per meter, because this is volts and this is meters. So, okay. So this is why this is a good problem, because of part A and part B. So feel free to ask questions. Feel free to use the chat box amongst yourselves. I'm going to set up our next quiz, chapter 28, quiz 1. Good. Some, but not all of you are done with chapter 24, quiz 8. Our first chapter 28 problem